Alright, so here's a follow-up question regarding latent heat. It says you put mass 1, that is 1 kilogram of ice cooled at negative 20 degrees Celsius, into mass 2, that is 1 kilogram of water at 2 degrees Celsius. Both are in a thermally insulated chamber. What is the final state of the system? For water, latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. Then we have specific heats for both ice and water. What is the final state of the system? And then we have a few multiple choices. Now, the first one's kind of silly, right? It says that we're going to have just ice. Probably not. And truly, it's in between everything melts, or we have a mixture of water and ice, because there is enough information for us to know. And we know that the water and ice will reach the same temperature eventually. So what we can do is, let's see how much energy would it take to melt all of the ice to make it into a liquid. And then we'll compare the available energy, meaning the energy which the water can provide. We'll see if that's enough. Now, we could start with the water to see how much we have. But of course, you know, my business background wants to know how much we need. What is our projection? That way we know we have enough. So let's start with that. How much energy do we need to melt all of the ice? And to know that, in this case would be energy required. That is to melt all of the ice. We'll have the energy required to undergo the phase change to melt all of the ice. And then we know that that'll happen when the ice reaches 0 degrees Celsius. So now we have to account for the energy required to have a temperature changing or going from what happened? Temperature from 20 degrees Celsius, I'm sorry, from negative 20, let's try it again, to 0. Meaning, again, this is a two-part problem, okay? Let me fix this. There you go. So let's see what we need. So 2 parts, right? We need latent heat for this one, and then we're going to use the specific heat capacity equation for this one. Okay. And let's start with our given, now that we know what is our first step, knowing how much energy we need to melt all of the ice. So given. We have mass 1, which is 1 kilogram, 1.0 kilograms. The board doesn't like me today. And that'll be for the ice, meaning subscript 1 will be for ice. And then we have temperature 1 initial, negative 20 degrees Celsius. And then we have mass 2, which is 1 kilogram. This is the water. We have the temperature initial of water, T2 initial, that'll be 2 degrees Celsius. And we have specific heat of ice. We're going to call that C1, 2090 joules per kilogram times degrees Celsius. Notice how we have kilograms this time. And then specific heat of water, we'll call that C sub 2, that is 4,186 joules per kilogram times degrees Celsius, and then we have the latent heat of fusion, which in this case is the same for both. And that is 3.33 times 10 to the 5th power joules per kilogram. Okay, there's our given. Now let's work on algebra. We said that we need to find the energy required to melt all of the ice. So that'll be Q1. First we account, let's try it again, it looks kind of silly. Let me use blue. Q1. We need to account for the phase change, so we'll have mass 1 times latent heat of fusion plus, now we have to account for the change in temperature, mass 1, specific heat 1 times delta T1. And here's where we have to state that the final temperature, in this case we want it to go to 0 degrees, that'll be the final temperature. I'm not writing it down as part of given because it'll change when we go for part 2. Well, it might change, right? That's going to be greater, so 0 is greater than negative 20. So temperature 1 initial. With that, we can write our equation this way. Heat required will be mass 1 times latent heat of fusion plus mass 1, specific heat 1, parentheses, temperature final, minus temperature 1, initial. Since our temperature final is 0, we can cancel it. And our equation would look like this. Mass 1, latent heat of fusion, plus mass 1, specific heat, temperature 1, initial. I can factor out mass 1, as you can see. Let's get some more room. So that'll be heat required equals mass 1, parentheses, latent heat of fusion, plus specific heat, temperature 1 initial. And now we can substitute. Wait. I almost made that mistake. It is a negative sign. There you go. There you go. Yes. So now, let's substitute our numbers, our values. Heat required will be mass 1, that is 1 kilogram, times latent heat of fusion. You know what? I needed a bracket here. Let's start over. We need a bit more space, more separation. 1 kilogram. Man, what's happening? Then latent heat of fusion, 3.33 times 10 to the 5th joules per kilogram. And that is minus parentheses specific heat of ice, that's 2090 joules per kilogram times degrees Celsius times negative 20 degrees Celsius. And that, well, these two negatives will make a positive. So I'm going to rewrite my equation. I think it's going to be the final form. That'll be, come on, heat required equals 1 kilogram There you go. Plus 2090 joules per kilogram times degrees Celsius times 20 degrees Celsius. Now let's use the calculator. It's gonna have, I'm going to include the 1 just so you can see it. 1 times 3.33 e function to the 5th power plus 2090 times 20. Looks good. So the energy required is 374,800 joules. So that's a big number. So that is our heat required. Okay? So let's write it down. Purple over here. So Q1 equals 374,800 joules. That is to melt all ice. That was the number, right? Yes. Okay, so now let's see we have enough. And to know, go back to our given. Now we're going to be looking at the water. Now, of course, the water is not going to undergo a change of phase because we know that heat flows from hot to cold. So only the water will give energy, or will transfer energy to the ice. So here's green. So that'll be Q2 equals mass 2, specific heat of water, times the change in temperature 2. And we know that the original temperature of water, which is 2 degrees, it's higher than 0, which is, we want to know that is all the energy that it can provide from 0 to 2 regarding the water. So then it'll be temperature 2 initial is greater than temperature final, which is 0 degrees. Now let's find out how much that is. So it'll be mass 2, specific heat 2. Oh, wait. Parentheses, temperature 2 initial minus temperature final. You can substitute, well, we know the temperature final is 0, so you can get rid of that. So we have heat required, well, heat available, in this case Q sub 2, mass 1, it is still 1 kilogram, times specific heat. You know what? I'm going to write it again just without the temperature final so you can see our final form of the equation. That's it. Now I'm going to substitute. As I said, mass 2 is 1 kilogram. Specific heat of water is 4,186 joules per kilogram times degrees Celsius times temperature 2 initial, that is 2 degrees Celsius. And let's see what that is. I know I do not need the 1. I'm including it so you can see it. So 4186 times the 2 degrees. 8,372 joules. That's all we have available. Of course, that's not enough. Think about it. If you wanted to purchase something and the price was $375,000 and you only had over 8,000, of course you cannot afford it, meaning this water will not have enough energy to melt all of the ice. it'll melt some of it, right? That is the energy that it's going to give out, that many joules. Meaning we're going to have ice and water. Because there's not enough energy to melt all of the ice. So Q2, was it 8,000? What? 372. 8,372 joules. Then the answer, because we need more energy than what we have, will be, there is a mixture of water and ice as the final state. Nice. Okay, so now what if we wanted to know the temperature of the water after, the temperature of the ice after the water has transferred all of its energy to the ice, meaning as the water went from 2 degrees to 0 degrees Celsius. Now this question it's not hard because we already have that number. That is the energy available. Based on conservation of energy, this energy released by the water, it's going to be transferred into the ice. Okay? Meaning, we know the heat required. All we have to find is the final temperature to then find the change in temperature. Okay? So let's start with our given. Now don't get confused. This question is talking about the ice, not the water. Okay? So we have heat required. I'm just going to write Q to not make it confusing. So 8,372, that is the energy available by the water, which is going to be used up by the ice. Mass of the ice, which is 1 kilogram. Then we have specific heat of ice, which is 2,090 joules per kilogram times degrees Celsius. Then we have the initial temperature of the ice, which is negative 20 degrees Celsius. And we're trying to find the final temperature to then find the change in temperature. Okay? And we can state the fact that we know that the ice is going to increase its temperature. It's going to experience an increase in temperature, meaning the temperature final will be greater than the temperature initial. So we have Q equals M1C1 times temperature final minus temperature 1 initial. Okay? So let's solve for temperature final. Give me a second. There you go. There's my mouse. So we have, let's get rid of that parenthesis so we can solve for temperature final. Minus okay, so I'm trying to solve for temperature final plus M1 C1 temperature 1 initial. This cancels. I'll use blue to show you what I'm doing over here. So then I have that heat required plus mass 1, specific heat, temperature 1, initial, equals mass 1, specific heat, 1, temperature final. I divide by the mass and the specific heat. so that it cancels. Let's do that over here. Now I'm going to write it strategically so I can simplify my equation. Both of them have the same denominator. So I'm going to break this apart, as it were. I'm pretty sure you're seeing why I did it. It'll make my equation cleaner because I cancel this. And finally, my temperature final equals heat required divided by mass times specific heat capacity plus the temperature to initial. Now we just substitute. Temperature final equals the heat available, the heat we had, which is 8,372 joules, divided by mass 1, that is 1 kilogram, times specific heat of ice, that's 2,090 joules per kilogram, times degrees Celsius, plus negative 20 degrees Celsius. I'm not going to do it again, but of course, I'm hoping you see that this will be a negative, these two, okay? So now, let's see what that is. So we have 8,372 divided by parentheses. Oh, well, I mean, it did not need the parentheses because it's 1. I'm not going to include the 1. Okay? Minus 20. That's about negative 16 degrees, 15.99. So negative 16, that's the final temperature. So temperature final, come on, for me at the end. Temperature final, come on, we can do this. There you go. Negative 16 degrees. One more. Guys, I don't know what's wrong with my board. Jesus. Okay, it's kind of legible. Now to find the change in temperature, we do delta T, which is, we had temperature final minus, where is it? Minus temperature 1 initial, so that'll be, we're going to need brackets for this one. No, you don't know, we don't. So, negative 16 degrees Celsius. Maybe because I'm touching the cable, huh? Celsius minus negative 20 degrees Celsius. That'll be a plus negative 16 degrees Celsius plus 20 degrees Celsius. So change in temperature equals 4 degrees Celsius. There you go.